In this video, we are going to discuss higher order derivatives. We have already seen what it means for a scalar valued function of a vector variable to be CK smooth. We make the analogous definition for a general map between Euclidean spaces. The definition is very simple. Definition. This is the definition of a CK map. CK smooth map. So as usual, let f from U to f be a map. As always, U is a subset of open subset of E. We say f is of class CK of U or is CK smooth on U if all partial derivatives of the components of f up to order k exist and are continuous. So in other words, if you just write f as f1 ... fm, then del alpha f I exists and is continuous for mod alpha less than or equal to k. Okay, so all the partial derivatives up to order k of the coordinate functions or the component functions of f1 to fm are exist and are continuous. Now this is a perfectly reasonable definition. It's straightforward and it's exactly the same as what is there for a scalar valued function of a vector variable. However, if you go back to the definition of the derivative in this general setting of a map f from U to f, there was no coordinates involved in the definition. The definition just used the fact that the space E and f were normed vector spaces. We did not use anything more than that. So artificially introducing coordinates in this definition, though perfectly reasonable, is not the most elegant way. Is there a way to define the notion of a CK smooth map in general without resorting to going to these coordinate functions f1 to fm? Is there some sort of intrinsic way to do this? Intrinsic is a word that means that uses only the structure of the given space and not anything more. Something that doesn't rely on something like coordinates. Essentially, what are f1 to fm? These f1 to fm come from the fact that you choose a basis for the vector space f, and in terms of that basis you can write the function f as f1 e1 plus f2 e2 plus ... fm em. This is what is a non-intrinsic or an extrinsic way of defining the thing. Now we want to see whether it's possible to define it in an intrinsic way. So this is going to be a bit abstract, and at first it might not be clear how exactly things are going to work. So we will first deal with the C1 case, and then let's just define what it means for a function to be C1 without resorting to coordinates, and then see the general case. So as a interesting aside, let me show you this famous picture. This is a picture from a 1888 postcard from Germany. This is a famous picture. You have probably seen this before. Depending on the perspective you look at, you either see an old woman's side portrait or a very young girl's turning her head and neck towards the side. So depending on your perspective, you see two different things, and suddenly your viewpoint shifts. So such a shift is going to happen. Now at first it might be difficult. There might be no easy way to see the perspective changing, but once it clicks, it will be very difficult to go back to the previous picture. You cannot unsee that this single picture represents both a young lady as well as an old woman. Okay, so that was just interesting aside. Let's write down the proposition for the C1 case and prove it, then move on to the general setting, which is a bit abstract. Okay, so this is the coordinate independent formulation of C1 smoothness, of being C1 smooth. Of course, there's one thing that I forgot to mention in this definition. Let me just fix it right away. F is said to be of class C infinity, or is C infinity smooth or just smooth without any further adjectives if it is Ck for all k greater than or equal to 1. In other words, this is just a somewhat opaque way of saying that all partial derivatives of all orders of the component or coordinate functions exist and are continuous. The continuity is in fact redundant, as you have seen when we dealt with scalar valued functions of a vector variable. Okay, coming back to this coordinate independent formulation of C1 smooth, let f from u to f be a function. Then f is C1 smooth if and only if f is differentiable and the map x going to dfx, this is a map that starts in u and maps to LEF. So think about this for a moment. Each dfx is a linear map from E to F. So if you consider the map that takes a given point x and maps it to this entire linear map dfx, you land inside the space LEF. Okay, so the map x going to dfx is continuous. Of course, if nothing is said, the topology, or rather the metric on LEF, is the metric coming from the operator norm. Okay, always we will put the operator norm on LEF. So being C1 smooth is exactly the same as derivative existing and this map x going to dfx being continuous. Okay, let's prove this. So I'm going to make a slight change to the hypothesis. I'm going to add, what I'm going to do is, I want to concentrate on the smoothness and not exactly on the derivative existing. So what I'm going to do is, I'm going to slightly change this statement, change the hypothesis. So what I'm going to do is, let f from u to f be differentiable, then f is C1 smooth if and only if the map x going to dfx is continuous. So I'm focusing on the C1's part, not on the differentiability. So I'm shifting over the differentiability to the hypothesis. Okay, this is a minor change. It's not that important, but it sort of clarifies what I want to capture. Let's prove this. The proof is not hard, but it's interesting. Proof. Now first assume f is C1 smooth. This means all partial derivatives of f exist, not of f, of the components of f exist and are continuous. Okay, now this just means that the matrix representation of f, that is the Jacobian matrix, has entries The entries are precisely the partial derivatives as entries that are continuous. Entries that are continuous. Okay. So if x comma y in U are suitably close, then the matrix of dfx minus dfy can be made as close to the zero matrix as desired. I'm being a bit loose here, hoping that you will be able to make this precise. It's rather easy to make what I'm saying precise. So since the partial derivatives are continuous and the fact that the derivative map, the matrix representation is going to be just the partial derivatives, if you consider the matrix representation of dfx minus dfy, that's going to be very, very close to the zero matrix if I choose x and y suitably close. Okay. So of course, I must write fix x in U. We fix x in U. So and here I must say if y in U is suitably close to x. That's the precise statement. If y in U is suitably close to x, then the matrix of dfx minus dfy is going to be each entry can be made as close to 0 as you desire. It immediately follows that if epsilon greater than 0 is fixed, then the operator norm of dfx minus dfy is less than epsilon if x and y are sufficiently close. This just follows because we have already established an inequality that involves the operator norm and the various entries of the matrix. It was an exercise to relate the operator norm and the various entries of the matrix. If the entries of the matrix are all very, very close to 0, then the operator norm can be made really, really small. Okay. So in other words, the map x going to dfx is continuous. Okay. So this takes care of one direction. Now suppose the map, I'm going to call this the map df from U to LDF, x going to dfx. Suppose this map is continuous, we have to show that the partial derivatives are continuous. Okay. Now observe that what this means is that if epsilon greater than 0 is fixed, then the operator norm, of course, fix x also, fix x in U, and if epsilon greater than 0 is fixed, then the operator norm of dfx minus dfy is less than epsilon. This is just the meaning of the map df is continuous. Okay. So if you act dfx minus dfy, so acting on the standard basis, it is easy to see that each column in the matrix representation of dfx minus dfy. So it is easy to see that each column in the is of Euclidean norm less than epsilon. Check this. Check. So what I'm doing is I'm acting dfx minus dfy on the standard basis, and I'm going to look at the magnitude of the resultant vector in the Euclidean norm. It will be less than epsilon. This just means that when you consider the matrix representation of dfx minus dfy, each entry is going to look really small, because each column, when you treat it as a vector, it's going to have magnitude less than epsilon, the Euclidean norm less than epsilon. So from this, the continuity of partial derivatives is immediate. Continuity of partial derivatives is immediate. Partial derivatives follows. Of course, I'm repeatedly using the fact that if a function is differentiable, then the matrix of partial derivatives is the matrix representation of the derivative map. Okay, excellent. We have got a coordinate independent formulation of the notion of C1 smoothness. If you observe, we did use the coordinate representation in the proof. We have used the coordinate representation in the proof. However, we have gotten rid of the coordinate dependence in the definition. Okay. I'm going to give you an exercise which should be very familiar to you by now. You must have solved variants of this before. Prove that any linear map between finite dimensional normed vector spaces is automatically continuous. Okay. So once you have done this exercise, what follows will start to make sense. So the setup is, you are given a map f from u to f. We want to define higher order derivatives. Higher order derivatives. So suppose f is differentiable, then as we have seen, we get a map df from u to f, which just takes an element x to the corresponding linear map dfx. Okay, so actually this is not df from u to f, this is df from u to lef. Okay, so you get a map that takes a vector and x and maps it to the linear map dfx, which is an element of lef. Now this map is from an open set into a normed vector space, right? A normed vector space, LEF. Now at this point, there are two ways to proceed. The first is to observe that LEF can be treated as a space of matrices, and as we have done before, we can identify matrices with Euclidean space and then define the higher order derivatives using the fact that this space is also an Euclidean space. We treat this map df as a map from an open set in an Euclidean space mapping into an Euclidean space, and you can define the derivative as usual. But that again is not so elegant, and it's somewhat coordinate dependent. There is a coordinate independent way of defining what it means for this map df to be differentiable, and that is the observation that when we define the notion of derivative, recall, one way of defining the derivative will be to take limit h going to 0, norm of f of x plus h minus fx minus dfx h by norm h. This goes to 0. Observe that in this definition, there is no Euclidean structure at all. All it relies on is the fact that both the domain and the codomain are normed vector spaces. In the numerator, we are taking the norm in the codomain. In the denominator, we are taking the norm in the domain. So really what is being used is the normed vector space structure, and the structure, the Euclidean structure, is not at all needed, at least to make sense of this definition. Except one change. In general, if you have a linear map dfx between infinite dimensional vector spaces, it need not be continuous. Linearity does not automatically mean continuity unless you happen to be in the finite dimensional case. Now the previous exercise will start to make sense. Why did we put that exercise? So this very same definition would have worked even for infinite dimensional spaces. Of course, you have to take dfx is linear. You have to put that as an additional you have to take dfx is not only linear, you have to take dfx as continuous when you are dealing in infinite dimensional spaces. That is not automatic. However, we are not going to take the most general case. I am going to give references to textbooks by Diodun and Lang. These textbooks have this in great detail. We are going to just treat the second derivative case in the Euclidean setting. That is a somewhat concrete case, and even here it's a bit abstract, and I will leave it to you to take care of the general case on your own. In your own free time, you can read up either Lang or Diodun's book or even Cartan's book to see this general setting. So let's define the notion of second derivative. Definition: let f from u to f be differentiable. Let df from u to LEF be the map x going to dfx. As usual, we say f is twice differentiable with we say f is twice differentiable if we can find a linear map which we are going to denote as d2f to denote the second derivative. We can find a map, I must say which point, f is twice differentiable at a if we can find a linear map d2fa from this open set u, from E. The codomain is what is complicated, it's LEF. We can find a linear map from E to LEF, and this linear map is automatically continuous. Why? Because we are in the Euclidean setting, so everything is finite dimensional, including the space LEF, which is automatically continuous, such that, and this is the crucial thing, so I'm going to shift over to a new page. Norm of dfa plus h minus dfa minus d2fa, the whole thing's operator norm, divided by norm h goes to 0 as h goes to 0. Okay, the map d2fa is the second derivative. So this is a coordinate independent formulation of the second derivative. So let me make a remark here. In the exact same way, higher derivatives can be formulated. So for instance, the third derivative is a map from E to this very complicated space LE of LEF. Okay, please ponder over this. Why do we get LE of LEF? Ponder over this and think about the higher derivatives. I'm not going to pursue this any further. I'm going to leave it to you to work it out yourself or refer to the textbooks that I have talked about. Now, this is very abstract and somewhat complicated. Let's try to understand this from a different angle. When you approach an abstract object through different angles, hopefully it starts to become concrete. So what we are going to do is we are going to analyze what happens. So this D2FA is a linear map from E to LEF. So what does it feed on? It feeds on a vector from E. Okay. So if you start with a vector from E, it feeds on it and it produces for you a linear map from E to F. Okay. So that's what this does. It eats up vectors in E and produces linear maps from E to F. Well, a linear map from E to F also eats vectors. So if you take this object, which is a linear map, and act it on a vector W from E again. Okay, what do you get? You end up with an element of F, right? Because LEF is a linear map from E to F. So you can think of this D2FA as eating two vectors from E, V and W, and producing a vector F in F. This should start to ring bells and light bulbs should go above your head. What does the linearity mean? Well, linearity in the variable V just means that D2FA V1 plus V2 acting on W is just D2FA V1 plus D2FA V2, this whole thing acting on W. This is just what linearity means. In a similar way, D2FA V W1 plus W2, this is using the fact that D2FAV is a linear map in LEF. This is just D2FAV W1 plus D2FAV W2. Haha, something nice has happened. This just says that D2FA is a bilinear map from E cross E to F, right? That's another way of looking at it. Instead of treating D2FA as a linear map from E to LEF, we can also view it as a linear map from E cross E to F. Okay. So already a lot of ideas have been exposed in this particular video. In the next video, I'm going to analyze when this map is going to be symmetric. Is this map symmetric? What is the meaning of is this map symmetric? Does it follow that if I treat D2FA WV, is this the same as D2FA VW? And this should be very familiar to you because we already proved something similar to this. We saw that if a map F is going to be C2 smooth, at least a scalar valued function, sorry, if you take a scalar valued function of a vector variable, and if it's C2 smooth, then the mixed partial derivatives are equal. Do mixed partial derivatives come into the picture? Well, we will see it in the next video where we talk about symmetry of the second derivative and also introduce the Hessian matrix, which is a concrete way of seeing what this bilinear map is going to be. So this video is a bit abstract and a bit difficult, so kindly watch this video again before moving on to the symmetry of the second derivative and the Hessian matrix. This is a course on real analysis and you have just watched the video on higher order derivatives.